And thank you all of you for being here on time. I'm here to present joint work with Will Ma, who's also in the audience. So you're welcome to pester him with questions after the talk. The work is titled Tight Guarantees for Static Threshold Policies in the Profit Secretary Problem. And since it's kind of a short talk that we have today, I figure if I can just explain to you the meaning of the title, then I've kind of done my job. Right? So we're going to start with the first question, which is what is the profit secretary problem? So the profit secretary problem, we're going to have n people arriving one at a time. And when each person arrives, we have to decide, are we going to accept them or reject them? Okay? Now, when someone arrives, we're going to observe the value of accepting them. And the value of accepting a set of individuals is just going to be the sum of the individual values. Right? The constraint we face is that we're only allowed to accept at most k individuals overall out of the n in total that will be presented to us. Right? Okay. So in addition, we're going to make some assumptions about these values. Right? So in particular, we're going to assume that these values are drawn independently from known distributions. So at the beginning of the planning horizon, we actually know the values, the distributions fi from which these values will be drawn, but we don't know the realizations. In addition, we're going to assume that the individuals are going to arrive in a uniformly random order. Okay. So you might ask, why is this called the profit secretary problem? I'm going to give you a short answer relating it to existing problems, because there's many, many similar problems that you've probably seen, especially if you're in this room, where we're kind of making sequential accept-reject decisions. And the key things that differentiate these problems are the assumptions you make, primarily about the values and what you know about them, and the order in which they arrive. Right? So kind of the classic secretary problem says, I don't know anything about the values, but I do know that they arrive in a uniformly random order. Right? Meanwhile, there's a large literature on profit inequalities, which generally says, actually, I know something about the values. I know the distribution from which they're drawn, but I don't want to assume a random order. They could arrive in an order that's not very favorable to me. Right? And so when you combine the secretary problem and this literature on profit inequalities, meaning we have known distributions and a random order, you get what's been called the profit secretary problem. And so this term was coined maybe about 6 or 7 years ago by a paper that some of you might know. You can also ask, why is that called the secretary problem and profit inequalities? But that's out of scope for a 17-minute talk. So that's the problem. That's the profit secretary problem that we're going to be studying. Okay, second part of the title, we're studying static threshold policies for this problem. Okay, what is a static threshold policy? It is literally the simplest, stupidest policy you could possibly imagine implementing, which is just, I'm going to set a threshold, t, and then I'm going to accept the first k people whose values exceed t. Okay. That's the class of policies we're going to be looking at. Why do we want to study static thresholds? Well, there's a lot of reasons, but keeping it short, I would say one reason is that these are very simple policies that we actually see people using in practice. Another reason is that because these are very simple policies, they're actually pretty simple to analyze. And as a result, we're actually able to get bounds that are better than the best previous known bounds, even for dynamic policies. And that's not because dynamic policies couldn't do better than these static threshold policies. Of course they could. It's just that dynamic policies are sufficiently complicated to analyze that no one's taken the time to actually prove better bounds than what I'm going to be telling you today. OK, so I've defined the profit secretary problem. I've defined static threshold policies. Especially for the people who are just coming in, let's walk through a simple example of this model just to make sure we've got it in our heads. So this is an example with 9 people. We're going to be able to choose at most 4 of them to accept. Right? Suppose we set a threshold of 85. And now the realized values are as follows, and they arrive in the order from left to right. Okay, well, only 2 people actually clear the threshold, so we're going to accept them both. And the total value we get is 88 plus 95. On the other hand, we might have said, well, shoot, we set too high of a threshold. We kind of had 2 wasted opportunities to accept someone. If only I'd set a lower threshold, like maybe 60, then on this same realization, notice that now 6 people actually have values exceeding our threshold. I can't accept them all, so I'm just going to accept the first 4, and then the last 2 are turned down. And so any questions about that example? Great. OK, so I'm 2/3 of the way through the title. right? We've got the profit secretary problem, static threshold policies. Now I need to explain what do I mean by tight guarantees. Okay, so we need some sort of benchmark to compare our performance against. So first, this notation, which isn't going to be that important, but the point is we want to say for any given threshold you set, what is the expected value that you're going to get from accepted applicants? And notice here, in this notation, I've removed the randomness from the values. So the only randomness in this is in the order in which applicants arrive. Okay, so this is the performance of my algorithm if I set a fixed threshold t. This, on the other hand, is the performance that I would get if I could perfectly predict or know the values and just take the k highest of them. Right, so I'm going to call this the omniscient benchmark. And so the natural paradigm that people in this field study is kind of what fraction of the omniscient benchmark can I obtain with a well-chosen value of t? OK, so what we do in this paper, we're going to give you some algorithms for choosing t. We're going to give lower bounds on the fraction of the omniscient benchmark that you can obtain by using these algorithms. So you'll always get a specific fraction of this benchmark. And then we'll actually provide matching upper bounds. So this is hence the word tight, showing that no matter how you chose t, there are some bad examples for which you couldn't get a better fraction than what we prove. OK, so time for a little bit of participation. Don't have a lot of time for this. But I think it's an interesting question. Suppose I told you this. I told you you're going to face a sequence of arrivals. You know something about the distribution of values. You have to set a fixed threshold t. How would you do it? Any thoughts on, like, it doesn't have to, you don't have to have any proofs in your mind. Just like someone gives you a couple minutes to think about it. What might you approach? What might you try? Yeah, Shadan.
K over n upper percentile.
OK, great. So if the values are IID, I would say, let me choose a fraction so that like there's a k over n chance that each value is a threshold such that there's a k over n chance that each value is above it. Because then, why do you think that might make sense?
Oh, I guess in general it would be whatever threshold, so that the probability that you have k values above that is a constant, something like that. OK, great. So you're saying maybe, say, the probability of having at least k values above your threshold should be some well-chosen constant. Yeah, I have. OK, great. Any other thoughts? Other ideas? Yeah, so I think this is a reasonable place to start. You say, well, I don't want the probability of having too many values to be too high or too low, so let's make it a half. A half seems like a good number. We're going to study some other closely related policies and then actually have an open conjecture about that policy. OK, the other question is, how much loss do we actually experience from the fact that we have to set this threshold in advance? Obviously, if we could see all the values, we could pick a threshold that perfectly picks out the k best people. So we want to know kind of how much loss could we experience. And the answer, of course, is going to depend on k, the number of people we can accept. Right? So if I can only accept one person, then the value to me of really learning who is the best, what's the highest value person is going to be very high. On the other hand, if I have 1,000 people I could accept, then I should be able to sort of predict with reasonable accuracy where the threshold should be, given that I have advanced knowledge of these distributions. Right? And so I wanted to just like take a quick by hand poll. If you had to guess, so it turns out that we're going to be able to get asymptotically close to 1 as k grows. The question is kind of what is our loss going to be? So it's going to be 1 minus something that depends on k. Do you think it's going to be exponentially decaying in k? So anyone who thinks loss is exponentially decaying in k, boldly raise your hand. OK. How about like 1 over k, inversely proportional to k? Nice. OK, a little bit of participation. 1 over square root of k. OK, we've got a lot of 1 over square root of k's. Great. So especially when you see central limit theorem, square root of k sounds good. How about something a little worse than 1 over square root of k, like square root of log k over k? OK, great. So how about you have no idea? OK. A lot of people don't have any idea. Yeah, so it turns out we get the exact answer for any k, which is this number, gamma k. It can be expressed as follows. 1 minus the probability that a Poisson is exactly equal with mean k is exactly equal to its mean. If you apply Stirling's approximation to this formula, it's approximately 1 minus 1 over square root of 2 pi k. So in this case, answer C was correct for all of those who chose it. Interestingly, if you're not willing to assume a random order, then answer D would actually be correct. OK, so let's just go a little bit more formally into the statements. The first theorem is an upper bound, right? So it's going to say, here's this number gamma k. We want to show that no matter how you choose your threshold, there are some bad instances where you can't do better than gamma k times the offline optimal. OK? And the bad instance actually has IID values. So I don't need to use the flexibility to have different heterogeneous distributions. And it basically looks like this. There's a low probability of some very high value item. Otherwise, the rest of the items have some sort of modest value such that it's high enough that I don't want to completely ignore them, but low enough that I don't want to just accept them and preclude the possibility of accepting this high value item. And then even if I kind of randomize about what to do with these intermediate value items, we show that if you choose your constants carefully, you can construct an instance where no static threshold guarantees more than gamma k. And so the details of the algebra are all in the paper, but I think not particularly important for this talk. But that's the nature of the bad example. OK, so then kind of maybe the more innovative part of the paper is coming up with a matching lower bound, an algorithm that actually achieves gamma k. Here's the first algorithm we analyze, which is for any threshold t, because you have advanced knowledge of the distributions, you can say, if I set this threshold, on average, how many people will I accept? And you might say, well, I want that to be not too small, right? Because I don't want to discard, but I don't want it to be too high, because if I'm accepting like k people on average, that means almost all the time I'm accepting k people, and maybe I'm going to miss out on some very high value items. And so it turns out, if you say, on average, I'm going to accept gamma k times k people, in other words, I'll accept a gamma k fraction of the maximum number I could accept, then that just works. That gets you a tight guarantee. Right? So that guarantees gamma k times the offline optimal. OK? Now, this algorithm is, I would say, pretty simple. But we can make it even simpler. So I think this is the first thing that I would have thought about when approaching this problem, which is that if I knew all the values, I would set a threshold so that k values exceed it exactly. Since I don't know the values, let's just set a threshold so that in expectation, k values exceed it. Now, it turns out if you analyze this algorithm and you say take k equals 1, you can construct bad examples where this doesn't do very well. It only gets a half, which is kind of known to be like easy to get in some sense. And so this doesn't get you an optimal guarantee of gamma k for all k. But we do exactly characterize its performance. And it turns out that for any k bigger than 4, this gets you an optimal guarantee. Exactly optimal. Right? So this very simple algorithm will get you an exactly optimal worst case guarantee as long as k is bigger than 4. If k is less than 4, it doesn't get you an optimal guarantee. Although if values are IID, then it does again. OK, so summary of what we said. Theorem 1 gives an upper bound. Theorems 2 and 3 give matching lower bounds for sort of simple algorithms that we describe. OK, so that's now I've kind of done what I needed to do in my 17 minutes. I've got like 3 extra minutes to tell you what excites me about this work. Right? So one is that the bounds are tight for all k. I'll talk about how that's not actually that common in this literature. A second is that I think even more exciting are I really like the algorithms we use for setting these thresholds. And finally, there's some intermediate results that we prove along the way that I think are independently interesting. So very, very quickly, I'm just going to skip through this slide. But here's a summary of related work. We have upper bounds and lower bounds for different problems based on different assumptions. In general, they're not the same. Right? We may have the order of growth right, but we don't necessarily know the constants. And so this is sort of unique in that way within this body of literature. Second, we are using simple algorithms. Right? So if I say demand is just the number of people whose values exceeds my threshold, then our algorithms all take the form of set some expected statistic of demand equal to some constant. Right? So for example, the first algorithm, the statistic is my utilization. So my expected utilization should be equal to some constant. As it happens, the constant we choose is gamma k, just because that's convenient for getting the right results. The second algorithm, even simpler, the statistic of demand is just demand itself. We set it equal to k, and we show what you can get. And then Schaden's approach, or Schaden's suggestion, was, well, maybe we could say like the probability of having extra, set that equal to a threshold, or the probability of stocking out, set that equal to a threshold. And in fact, a number of papers on related problems have used this summary statistic to set their threshold. And so a natural question is, if we set expected stockout probability, or stockout probability equal to an appropriately chosen constant, will we get an optimal guarantee? I conjecture that the answer is yes. We haven't proven it yet. So if you're interested in working in this space, that would be kind of a nice, I think, fairly tractable open problem to work on. OK, final thing I want to tell you about is this sort of intermediate result we used along the way. So I want you to think about the following problem. We're going to flip n coins. They each have some bias. We're going to flip them independently. Okay? Now, based on the realized number of heads, you're going to get some reward. So if the realized number of heads is d, you get reward f of d. Okay? F is given to you. You get to choose the biases of these coins. You get to choose the probability that each comes up heads, but not completely unconstrained. That would be kind of a boring problem. So I'm going to give you some constraint on the expectation of g of d for some function g. So the simplest form would be like the mean number of heads has to be equal to some constant. So it turns out, when you have problems of this form, for any f and for any g, no structure needed, there's always an optimal solution with the following simple form, which is that every non-deterministic coin, so every coin that actually has uncertainty about which way it's going to come up, has an equal probability of coming up heads. So this is a really nice result that I think would be useful well beyond the application in which we use it. Because it's saying if you have any optimization problem of this form, you can restrict your search space to assuming that d is just a constant plus a binomial distribution. OK, so to close, like I came to this problem basically purely as a math problem. Right? I thought it was kind of interesting, see what we could do, see what we could prove. Much to my surprise, I think it might actually have applications. And so the reason for this is that these algorithms are actually used all over the place. Right? So if we think about it, in many contexts, we set some rules about who's eligible to receive a service. And then within the eligible population, we just allocate first come, first serve. So one area that I work in is affordable housing. And there, you'll often have income eligibility. Like to qualify for this program, your income can't be too high. But I don't take someone with an income of $16,000 and necessarily prioritize them over someone with an income of $17,000. Right? I just have a first come, first serve among the eligible population. And that's also what we did for COVID vaccines last year. Right? We would often have policies like anyone over 65 is eligible to be vaccinated in the state. Now it's a mad scramble to see who can book the appointments. So we see that these policies are used. Then there's a question about the assumptions. I think in general, the assumption that we know something about the distribution of values ahead of time is a reasonable one. I think the question of whether values are random or not, and whether it makes sense to model them adversarially, that's kind of more context dependent. And so what we show in our work, in some sense, is that actually you do get much better bounds if you're willing to assume random order. So the purple and green lines are the best known bounds when you have an adversarial arrival order. The red line is kind of the improved bound that we get by assuming a random arrival order. So it really is much better. I think I'm out of time, so I'll leave it there. And I think we have another speaker, but if anyone wants a question while they set up, I'm happy to answer.
Yeah, so I'm curious as to what progress you can make on the open problem stockout probability. I think you mentioned really great a couple slides ago.
Thank you.
Great
Yanai,
question.
if you have a question, you can go.
Yeah, sorry, go ahead.
There was some weird interference. So I think it's actually a quite tractable open problem. We just haven't kind of taken the time to dig into it. Some of the tools, like the one I used at the end, could be directly applied to this problem. But then there's still some sort of messy algebra to grind through to see if it works. And we haven't done that. So we tried to construct counterexamples and failed. So I think it is true, but someone needs to prove it.
All right. Yeah, thanks. I think in the interest